Very nice. So, yeah, so the topic of my thesis was that I tried to quantify the quality of city cycling in a way using big mobile activity tracking data. And well, so first, let me maybe explain the background of this work. So among cyclists, both ambitious professionals and also leisure cyclists, it becomes more and more common to use these tracking applications just to record the training and monitor their training. And with these tracking applications, a lot of data is collected, vast amounts of GPS tracks, most importantly, and this data contains important information. And with the right methods, we are able to extract this information, for example, on the quality of the cycling infrastructure of a city. And this information could support the work of city planners, for example, helping them to identify obstructions in the road network. And then if they can improve the infrastructure for cyclists, it benefits the cyclists again and closes this cycle. Of course, this is an ideal scenario and not quite yet the case. So in my work, I was working with more than 50,000 GPS trajectories recorded with the mobile tracking application Sports Tracker that you might have heard of already. So the trajectories were collected between 2009 and 2013 in the Helsinki metropolitan area, and we received them as part of a data agreement. Now, in the title, it says big data and these 50,000 GPS trajectories. This is not really big data in volume, but I'm still talking about big data because some of the characteristics are the same as they are common for big data. Most importantly, we have this unprecedented spatio-temporal extent and resolution of the data. But then we also have challenges that are commonly associated with big data. For example, the data has only limited representativeness, so these cyclists that use the application cannot really represent the whole population. Then we are having a participation inequality, which means that very few cyclists account for a large share of the data. And we have uncertainties, for example, GPS uncertainties. Then I also found a large divide in the popularity of the infrastructure. So that most streets are either very popular with cyclists or only very, very few cyclists are using these, which also limits the usability of the data. And then, of course, there is the limited availability of the data because this data is hard to obtain because, of course, it is personal information and we need to protect the privacy of the cyclists. So in my study, I aim to use this data to derive the so-called cycling traffic fluency. And cycling traffic fluency means the smoothness of bicycle traffic flow. So the idea is that a cyclist travels fluently if he or she can travel seamlessly at a comfortable speed without having to decelerate or even halt without wanting to do so. So I identified 4 properties that are related to this fluency. First of all, the relative speed of the cyclist, so their speed in relation to their usual traveling speed. Then the acceleration of the cyclist, the frequency of stops, and the duration of the stops. So to derive this information, I cleaned the trajectories, I smoothed them, and matched them to the road network, which was beforehand obtained from OpenStreetMap. And this street network was segmented into segments of around 25 meters length. Then the trajectories were split into sub-trajectories where each sub-trajectory is associated with one street segment. And then for the sub-trajectories, I calculated the properties, for example, speed and acceleration. And then I aggregated these properties to these street segments and obtained the segment characteristics that now describe the behavior of all of the cyclists on this particular segment. And then these segment characteristics were combined to the final measure, which I call the cycling traffic fluency index. So these characteristics, these segment characteristics, are at first normalized by transformation functions, so that they then reflect the indicated fluency. So let's take, for example, acceleration. When cyclists travel with an acceleration close to 0, this acceleration index will show very high values, because acceleration values close to 0 correspond to a quite fluent behavior. But then this transformation function penalizes braking and also very high accelerations, because they correspond to less fluency. And then all of these normalized indices are combined in an intermediate step to 2 intermediate indices, one for these movement-based characteristics and one for the stop-related characteristics. And those 2 are then again combined to this final fluency index using the harmonic mean, so that both constituents, so this component and that component, have both to be high in order for the fluency index to be high as well. Okay, but now on to the results. So here you can see finally the fluency that I found from the data on the streets of central Helsinki. Bright colors indicate high fluency, and where you can see only these plain gray lines, these are the streets where we did not have enough data to aggregate a reasonable value. So unsurprisingly, very low fluency segments accumulate at intersections, but also close to some points of interest, which suggests that there is maybe some influence of voluntary behavior of the cyclists, which has nothing to do with the traffic conditions. But then again, if you look at this very central part, there we have also a considerably lower fluency values than in the surroundings. And it is also so that cycling on dedicated cycling infrastructure, for example, cycle lanes, appears more fluent than on street or on shared walk and cycle paths. So the evaluation of this data is difficult. And my approach was that I compared the components of the cycling traffic fluency index to auxiliary data. First of all, I used a data set of trajectories that were recorded by a volunteer. So these trajectories were not part of the original data set, and I combined the properties of these volunteer trajectories to the segment characteristics of the traversed segment. So for example, in this graph, you can see in blue the relative speed of this volunteer compared to in orange the corresponding aggregate speed of the segments. And as you can see, there are the very same patterns repeating in both lines. And so this suggests that these segment characteristics are indeed suitable to some degree estimate the situation on the road. And then furthermore, I clustered the stops that I found in the data to so-called stop hotspots. And these stop hotspots also show a high correspondence between them and intersections, but also other obstructions, for example, stairs. And we also find some stop hotspots close to points of interest, also to viewpoints, for example, down here, right, at the coast. And again, this suggests that there is some behavior that is not related to the traffic conditions, but to voluntary behavior of the cyclists. Now, to conclude this presentation, I can say that this process that derives this information on cycling traffic fluency scales linearly with the number of trajectories. So that is also applicable to larger data sets, and it is also applicable to other data sets. So for example, data from other tracking applications or other regions with maybe some adjustments on the processing methods. Then the cycling traffic fluency index is an example of how these different characteristics can be combined, but this index can also be flexibly modified by, for example, changing these transformation functions. And in doing this, the index can be applied to different applications which might require different configurations of the index. And as it was already said, the two main areas of application are, first of all, the city planning, as the index could be a decision criterion for city planners, helping them to evaluate the cyclability of the road network. Or then it could also be used as a cycling quality-centered routing criterion, helping individuals to plan their routes most fluently. So thank you very much